Welcome to Advanced Quantum Chemistry and my third lecture on Hartree Fock theory. In the previous lecture, we asked ourselves what can we use the orbital energies for, because we learned that summing the orbital energies as an approximation to the ground state energy was not a good idea. The answer to this question is Koopmans theory. Let's look at an ionization process, a process where we remove one electron from the system, and in Hartree Fock theory that means we remove one electron from one of the occupied orbitals, and let's here now assume that we remove the electron from the spin orbital K. As a consequence then we get an determinant which has one electron less, so we get an n-1 electron determinant, and the n-1 electron determinant, if we remove the electron from the spin orbital psi k, is missing the spin orbital psi k. So between psi k minus 1 and psi k plus 1, we don't have the spin orbital psi k any longer. And in the simplest approach, which we use here, we assume that all the other orbitals are not changed. So we use the spin orbitals which we have obtained by solving the Hartree Fock equations for the n-electron system with all n electrons. And then we just write up a Slater determinant where we don't include the spin orbital from which we have removed the electron. The ionization potential, which one, for example, could measure in experiment, is then the difference in the energy of the ionized system, so the n-1 electron system, and the energy in the original n-electron system. And in this simple Hartree Fock-based approach, where we keep the orbitals frozen, as said before, we describe the n-electron system with the normal Hartree Fock energy, and we describe the energy of the n-1 electron system by calculating the expectation value of the Hamiltonian with this n-1 Slater determinant, n-1 electron Slater determinant, up here where we just have removed the spin orbital psi k. So it's the difference between this expectation value and that expectation value. Now this one, the second one, that's just Hartree Fock energy, which we have seen now several times before, here with the kinetic energy and electron nuclear attraction part, and here with the averaged electron repulsion. Now for the n-1 electron system, we have in principle the same expression for this expectation value of the Hamiltonian. The only difference is that we have one spin orbital less. So here in the sum over all occupied spin orbitals, we have to exclude the spin orbital k. And again here in this double sum, we also have to, the double sum over I and j, which are over all occupied spin orbitals, but that should not include the spin orbital k. So we exclude spin orbital k here and there. If we now subtract the two from each other, in order to calculate the ionization potential, then we get minus here the kinetic energy and electron nuclear attraction integral. And for the electron repulsion terms, we get two contributions. We get one where the original sum over j here, we only have k left, that gives this integral, and we have still all occupied orbitals for I. And vice versa, we get it where the orbital I, we only have k left, whereas we still have all occupied orbitals j. But remember, this is a sum over all orbitals, all occupied orbitals, and whether we call them I or j is completely irrelevant. So we can, as the first thing, we can rename j here. We can rename that to I, and then as a second, one should remember that, I mean, this is pk of electron 1, psi I0 of electron 2, and obviously we can interchain electron 1 or electron 2 in those integrals. That gives the same, which means that this integral is actually the same as this integral, and this integral is essentially the same as this integral, so we can combine those two sums in order to give this one sum. And now we can recognize this whole expression as nothing else than the orbital energy k. And that means in this simple approximation, Hartree Fock based approximation, where we describe the ground state with the Hartree Fock energy, also the n electron state with the Hartree Fock energy, and the ionized state also with an Hartree Fock energy, but just calculated from a determinant where we removed that single occupied orbitals without adjusting the other orbitals. Then if we calculate the ionization potential in this way, the ionization potential is actually minus the orbital energy of the occupied orbital from which we have removed the electron, which means to ionize an electron, we have to use precisely as much energy as the orbital energy was. And this is Koopmans' theorem. Now, we also can look at something which is called electron affinity. That's the opposite process. That's a process where we not remove an electron from the system, but we add an electron to the system. So the electron affinity is calculated as the energy of the n electron system minus the energy of a system where we have added one electron. And in the same way as we have done that, we are going to add one electron to one of the virtual orbitals, virtual orbital A. And if we would do the same calculation as before, we would find out that in this Hartree Fock based approach, the electron affinity is just minus the orbital energy of the virtual orbital A. Now, and that's called Koopmans' theorem. Now, Koopmans' theorem, of course, is an approximation. And there are two reasons why it's an approximation. First of all, it's this frozen orbital approximation, which means that we, for the n+1 state in the case of the electron affinity and for the n- state in case of the ionization, we use just the same orbitals as we have obtained as eigenfunctions for the n electron systems. So the orbitals are not allowed to change or not allowed to relax. So it's a frozen orbital approximation. And that of course means that the energies which you calculate for the n+1 or n-1 wave function are too high. Because if we would allow the orbitals to be changed, to be optimized, then because of the variation principle, we will get a low energy. So those two energies are too high. The second reason why it's an approximation is that we only use Hartree Fock theory. So we have not included electron correlation. Now the electron correlation effects are larger the more electrons we have. And that means in the case of the ionization process, the electron correlation effects are larger for the n electron system state, and since we do not include them, the n electron energy is too large. And that means for the ionization process, we have that the n electron energy is too large in this Hartree Fock approximation, but because of the frozen orbital approximation, also the n-1 energy is too high. So both energies are too high, which means we make an error of the same sign in both energies. And these errors partially cancel when we calculate the ionization potential, which is the difference of the two energies. And therefore, Koopmans' theorems is very good for ionization energies, where we calculate the ionization energy as minus the orbital energies. But for electron affinity, we have that the n+1 electron wave function has too high an energy because we did not allow the orbital to relax. But it also has too high an energy because we did not include electron correlation contribution, which means that for both these approximations lead to that the n+1 energy is too high, so the errors add for the electron affinity, and therefore Koopmans' theorems values for the electron affinities are not really good.